Hello, everyone. Welcome back to ChaosWest TV. The next talk will start momentarily. I will now switch back to German for a few seconds to announce the translation. Then I'll switch back and then we'll go off to the races, as they say. So, nochmal schnell auf Deutsch. Willkommen zurück zu ChaosWest TV, eure beste Bühne auf dem RC3. Der nächste Talk beginnt gleich. Er ist zwar auf Englisch, wird aber wie so vieles dank unserer Übersetzungscrew auf Deutsch übersetzt. Ihr solltet in der Lage sein, das im Stream einfach auszuwählen, ohne größere Probleme. Und dann könnt ihr den Vortrag auch direkt simultan übersetzt auf Deutsch hören. Und ich rede jetzt auf Englisch weiter. Alright, back to English. Now, in the comfort of your own homes or wherever you're viewing the stream, please do a warm round of applause for our next speaker, Martin, who will talk about optimizing public transport. Let's go.
Welcome to my contribution to this year's RC3 2021 in the form of this talk, Optimizing Public Transport, a data-driven bike-sharing study in Marburg. I would like to thank the organizers of the RC3 2021 for organizing the whole event, and in particular, I would like to thank the channel that accepted me, ChaosWest TV, for accepting the presentation of my work. Today I would like to give you a quick overview of one of my hobby projects in which I scraped and therefore downloaded over 1 million data points regarding the bike sharing system in the city of Marburg. This study came about when I was traveling from Stuttgart to Frankfurt and ultimately to Marburg some time ago, and I was watching the amazing Spiegelmeining talk by David Kriese, so thank you very much for this implicit inspiration of the work that you're about to see now. Who am I? My name is Martin Lellep, and I studied physics in the past, and actually I continue to do so in the form of a PhD in theoretical physics at the University of Edinburgh in Scotland. And in my spare time, I like to do data analysis of all kinds of data. There are two more things that are important for here now. It's first of all, I studied at the University of Marburg, obviously in Marburg previously, and then also I like to ride my bike. Marburg, for those who don't know it yet, it's a small university-dominated town that is in the north of Frankfurt am Main, roughly 80 kilometers, so an hour by car or an hour by train approximately. And again, it's quite dominated by the university that is located there, and that can be seen simply in terms of, for instance, numbers. There are roughly 25,000 students for an overall population of 77,000 residents in total, which is quite substantial, obviously. You can see a quite popular picture here of a picturesque scene in Marburg. You can see the castle and then the river Lahn, as well as a few houses and a bit of green. And the bike rentals are currently provided at the time of recording this by the company called Nextbike. Before now diving into a bit more technical details, I would like to motivate my story or my study by the story of Anna. Anna is a university student at the University of Marburg, and she lives a bit outside the city. So she typically does not walk to the places she needs to be or study at, but she takes a bus from her flat to the city, and then does the last mile by walking or cycling or whatever. And she's also quite eager student, so she very often studies quite late, as you can see here. That's a picture of a late Marburg, so to say. And just as it happens now, she needs to catch a bus now because she's a bit late. She forgot to pack in her fancy MacBook in time, so she needs to hurry up a bit and, didn't really make it. So therefore she thought maybe taking a Nextbike for the last mile to the bus station is a good idea, so she can safely take then subsequently the bus home. And normally the Nextbike stations look like that here, so there's plenty of bikes. It's very easy to go there, grab a bike and go to your destination. Now, Anna must be a very unlucky student today because she arrives at the bike station and it turns out that the station is empty. So ultimately she misses at least this bus and therefore only arrives at home a bit later. Her cooking plans and her Netflix plans, all that stuff is postponed a bit because, well, she arrives a bit later. And that's, of course, a very, very sad story. Maybe it happens to multiple people, not only Anna. And in fact, it also happened to me a few times. And every time it happened to me, I thought, well, I must be the most unlucky person in whole Marburg. Going to a normally completely fully packed bike station, and now it's completely empty, missing, for instance, subsequent public transportation. After it happened to me a few times, I thought, well, maybe I'm not that unlucky. So is there maybe a system to empty bike stations in Marburg? And given now my spare time interest of analyzing and capturing data, I thought, well, data to the rescue, of course. And therefore the idea for this talk now was to build a web scraper in order to acquire Nextbike data, collect the data, store the data, analyze the data, and then hopefully finally help Anna, me, and other students to figure out which stations maybe to avoid and which stations are safe to go to if you're in desperate need for a bike. The tech stack that I'm using here, it's based on a Docker container in which a Python scraper runs every 30 seconds that queries the Nextbike API. It downloads the data, it parses the data, and then it saves the data outside the Docker container in order to be evaluated later on. And it turns out that the whole concept of what I just described also has a name. It's called Extract, Transform, Load Pipeline, or ETL in short. And what I, again, wrote here is an ETL pipeline in Python, and then I wrote an analysis code also written in Python. And all that was running on a small home server in my flat. The data that I captured consists of the bikes identified through IDs and then also the locations of those bikes, typically at stations, but some of them were also freestanding, and last but not least the station locations, and of course obviously also a list of stations. And then with that I went ahead and did a few pictures that I'm about to show now and a few analyses. And if you're interested in that, there are slides available on this website here. The website can be reached through the QR code or through that link. And this website contains the slides that you're seeing here, high resolution figures, a few interactive figures, and all the information on previous blog articles that I wrote about this topic. So the results of Anna, first of all, to start slowly, it turns out that there are 37 bike stations in Marburg with roughly 230 bikes spread across the whole Nextbike Marburg ecosystem. And it's now, knowing that there are roughly 40 stations, it's quite interesting to see where these stations are, because then Anna could, for instance, already go to another station if one station is empty. And what you can see here is now a map of Marburg where the stations are annotated by these dots, and the area of the dot, as well as the color code, corresponds to the average number of parked bikes at that station. So let's see an interactive version because it's a bit nicer to see it in that way. So I click on here. Okay, now we can pan around and zoom, as you can often do with these interactive graphics. And also by clicking on these buttons or on these points, you can see the station name as well as the average number of bikes placed there. And it becomes quite obvious that, well, most of the stations are in the central part of the city, a few in the outskirts here, and it turns out that the largest station in terms of the number of parked bikes on average is the main train station, Hauptbahnhof. There are again a few more spread around the central part of the station, such as the Elisabeth-Blochmann-Platz, which is the second largest station. And then if you continue the train line here, you can see that there's actually another set of stations where the secondary train station is. So that's another train station, a smaller train station. Okay, so the first result for Anna would then be a day-hour usage histogram, because it's the kind of the first order approach, I would say, in order to see how the ecosystem of Nextbikes is in use against day as well as hour. And therefore Anna will, based on this figure here, she will understand when to maybe plan for a bit more time when looking for a bike in a desperate fashion. And since this figure is a bit more difficult to understand, I would like to take a moment to explain it. And we are going to start with the top figure here. What you can see on the x-axis is the hour of the day, and on the y-axis, and that's shown in the whole figure. So each of the numbers that you see is the following. It's the average, it's the number of parked bikes, and then you subtract the average of the number of parked bikes in the whole ecosystem of Marburg. So that means if a number of 0 is encountered, like roughly here, it means that it's the average number of parked bikes simply in the system at that point in time. When the number is larger, it's above the average. If it's smaller, it's below the average. And you can clearly see from this small figure here already that in the morning, more bikes are typically parked. And then in the evenings or around noon, you can see 2 dips, a bimodal distribution, so to say, where people, obviously use bikes around noon and 6 p.m. roughly, where these used bikes, of course, are not parked, and therefore these numbers are small. And the same thing can be done for the day of the week. Here and here you can see that the Monday, the beginning of the week and the end of the week, meaning Monday, Tuesday, and Saturday, Sunday, are a bit more popular. So more people ride a bike, and therefore fewer bikes are parked, and therefore this is negative. And then in the middle of the week, fewer people seem to ride the bikes in general. And if you combine these figures now, you can see the joint histogram here, where you can not only look for time or day separately, but also in a combined fashion. So you would, for instance, see that Monday morning is a time where many people use bikes because there are not as many bikes parked. And then also on a Saturday, you can see the same. So in the around afternoon, many people seem to use the bikes. Last but not least, on Friday mornings, it's quite easy to get a bike because many bikes appear to be parked, maybe because people envision already the weekend. So that's the first outcome for Anna. Try to avoid times around 6 and around noon when desperately looking for a bike. And now the even more interesting part for Anna is the probability to find a specific station to be empty. For that, I took the time series of the number of parked bikes and counted the occasions where there was no bike for each of the stations here. And that has been done again for each station separately. So for each station at the end of the day, you get a number that denotes the probability of finding that station empty. And clearly, for instance, the Hauptbahnhof, the main train station, which was the largest station, it's quite unlikely to find it empty. And contrary, if you go to these stations down here, for instance, the Amplan Wirtschaftswissenschaften, it turns out that these are empty at about 70% of the time, which is quite substantial, I would say. And interestingly, if you now look for the secondary train station in Marburg, the Südbahnhof, you can see that this has quite a substantial probability of running empty at about 30 to 40%. In particular, in comparison to the main train station, which is essentially almost never empty. Also interestingly, you can then plot these probabilities against the average number of parked bikes at the station, and you find an anti-proportional relation between those two. It means that the larger the station, the more unlikely it is that it is empty, which is quite a reasonable outcome, I would say. So finally, to conclude for Anna, she should try to avoid small stations, and in particular, she should try to avoid the stations that are, annotated here with a sad smiley, because these tend to run empty quite often. Okay, so I have all this ETL pipeline stuff already set up. I have collected over 1 million data points, and then I thought, maybe there's more in the data than only helping Anna. So everything that I've shown you so far, it's from the perspective of a user. And now I would like to turn towards the perspective of a city. And there I would like to ask a few questions like, how is next biking used in Marburg, first of all? And then in general, is cycling a good thing for a city? How can cycling contribute to a better city? And now better is, of course, first a quite vague term. And then last but not least, is it worth improving bike infrastructure for a city? And all this, again, is now from the perspective of a city instead of the user. The first thing that I would like to start with is something that I call the distance matrix, in which I concentrated on the positions of the bike stations and computed the pairwise distances for all of them. And since the distance is of course symmetric, also the stored matrix is now in the end also symmetric. And it turns out that there are roughly 600 combinations, and these combinations can be shown in a symmetric matrix as shown here, where on the x-axis, this one here, and the y-axis, you can see the stations, and then each combination denotes the distance between that one station and the other station. It turns out that the range of these distances is between 0 and roughly 9 kilometers, and of course those that have a 0 distance to other stations are essentially the stations themselves. So if you pick a station, obviously the distance to itself is 0, and therefore the diagonal is exactly 0, and then again all the remaining part is a symmetric copy of the other diagonal part. The other thing, and that is now the main treasure, I would say, of this study, so the main base for everything that follows, is what I call the transition matrix, where I counted the number of transition of bikes from one station to the other station. That is now, of course, not symmetric anymore, because just because, say, 5 bikes go from one to the other station, it does not mean that these 5 bikes really come back again. And therefore, the number of entries is roughly 1,400. Again, it can be shown or visualized in the same fashion. So you again have the stations on the one axis and the same stations on the other axis. And now each entry here in the matrix corresponds to the number of transitions of bikes from one to the other. And the range is from 0 to over 3,000. And it turns out that actually the self-transitions, meaning somebody takes a bike from a station, does something with a bike, maybe grocery shopping or so, and then the person comes back to the same station, these events occur the most frequent, and therefore the largest entry are on the diagonal typically. Sometimes it's not so interesting what happens regarding the self-transitions, and therefore another matrix can be derived from the first one, namely a transition matrix without diagonal elements, where those elements have been set to 0, as you can see here, if you look closely. Speaking of looking closely, it's quite educational if you not only see the figures, but also can explore them a bit, and therefore I rendered an interactive version of it. Let's visit it. So that's now again the matrix without the diagonal and one with the diagonal. And now by hovering over these entries here, you can see that, for instance, from Am Schülerpark to Ockershäuser Allee, 0 transitions happened. And then a bit larger one, for instance, Biegenstraße to Hauptbahnhof, over 800 transitions happened in the time of capturing the data. So feel free to explore a bit, maybe identify the most interesting, most used popular routes. Okay. Such a transition matrix can actually also be shown as a network graph, where here I concentrate only on the largest entry, because it turns out the full transition matrix is a bit too dense. And what is shown now here is, as blue circles, it corresponds to a station, and then these edges here are drawn whenever there happens a transition. And you can already see here that there are a few stations that are quite isolated, like those, and then many stations have a self-transition and mostly feed to a more central station. And since that is also more interesting in an interactive fashion, I also rendered an interactive version of that. Now again, we can zoom, pan around, and drag the graph around a bit. And interestingly, if you click on a station, you can see from where transitions happen to that station. So like those interconnected central ones, like the Hauptbahnhof, the main train station, it's quite connected in the graph. And then there are a few like Friedrichsplatz, which are not connected at all. Interestingly, that one here, for instance, the Aföller Café Trauma Aföllerwiesen, it doesn't even have a self-connection. So it turns out that, well, people apparently mostly use it for taking a bike going into the city. And most dominantly the Elisabeth Blochmannplatz, actually. Okay, so if you now take these transition matrices as well as the distance matrices into account and mix them, first of all, you can get a few interesting numbers. So here I calculated the overall number of trips, which turns out to be 210,000 trips in the time of capturing the data, which is quite a substantial number for such a small city like Marburg. And this is, of course, computed by taking the sum of the transition matrix elements. And then if you weight these sums or these entries with the distances between those stations, it turns out that those transitions or those trips essentially correspond to a distance of 320,000 kilometers that have been traveled, which is a few times around the Earth, actually. Now, when these two basic numbers and the matrices that I introduced earlier are combined with a few statistical details, like, for instance, the average consumption of fuel of a car or how much CO2 it produces while driving, a few ecological, economical, and social benefits of a bike system or cycling in general can be derived. First of all, I found it quite entertaining that the overall number of calories burned corresponds to 8.7 or 8.6 million kilocalories. And to convert that to a bit more, well, real-life number, I would say, I calculated how many Nutella jars those are, and it turns out that it's roughly 4,000 Nutella jars that have been burned in terms of calories just by this system of cycling. And then also, it can be found that this distance here, if you would have driven it by a car, you would have, well, used almost 26,000 liters of fuel. You would have produced 40 tons of CO2, and that fuel that you would have bought would have cost 34,000 euros, actually. Interestingly, that number here of 40 tons of saved CO2 corresponds to an average German who lives for 4 years, or 4 Germans that live for 1 year. So a typical German produces roughly 10 tons, and therefore it's 4 times that, obviously. Okay, so again, from the transition matrix, you can derive a few more interesting details, like, for instance, details that are interesting from the perspective of traffic management. Like here, I calculated the most popular routes by finding the maximal elements of the transition matrix, and it turns out that the most popular route has been used well over 2,000 times here from the Hauptbahnhof to the Ginseldorfer Weg. And if you look closely, you can see that the main train station, or the Hauptbahnhof, as well as the Elisabeth-Blochmann-Platz, is involved in many of those top routes. And that's now, again, interesting. For instance, if a city would like to improve the bike system, because we've now seen it has quite a good impact for social, ecological, and economical aspects. But let's say the city has maybe limited financial resources. It would be interesting to simply calculate the most popular routes and then start fixing or improving them first. Okay, now at that point you might ask yourself, well, what kind of data did he scrape? And for that I would like to show you this graph. It shows the number of parked bikes in the whole ecosystem of Marburg against time. And as you can see, I did it in 2 batches. The first one has been obtained from March to December 2020, so last year. And then I restarted the scraping at the end of April and finished just a few days ago in December 2021. And you can clearly see that the number of parked bikes decreases when the weather is good, or when there are summer months, and therefore most likely because the weather is good. And of course it suggests itself a bit, given that I captured this in 2020 and that one here in 2021, and taking the corona pandemic into account, well, how does it compare? And therefore I concentrated on the overlapping month of the 2 data sets and calculated, well, the comparison, as you can see here. Now in blue it's 2021 this year, and 2020 is shown in red, and you can see that the number of parked bikes increased, actually. There might be a multitude of explanations for that. I don't know, maybe one explanation could be that people took more advantage of working from home. Okay, so everything that I've shown you so far, it's been mostly statistical statements, averages, sums, and stuff like that. And now I was interested if it's possible to do also more precise predictions. And therefore I turned towards a machine learning or artificial intelligence task, where I try to predict the number of parked bikes, meaning the quantity that are shown over and over again in the last few minutes. So is it possible to predict that number based on the hour of the day, the weekday, and the temperature that is shown here for 2020? And when starting such a task, it's always, first of all, very useful to investigate the training data, and therefore, I try to plot it. And because it's a three-dimensional phase space, it's also very simple to plot it. So you can essentially plot it as a scatter plot, and the color coding here has been chosen to denote the target variable, meaning the number of parked bikes. And just by inspecting the data, you can already see that the smaller the temperatures are, the more bikes are parked, and therefore the fewer bikes are used. I use a random forest machine learning model, which is an ensemble model of decision trees, of randomized decision trees. And this model is quite powerful because it can work with little data, it can work with a lot of data, and it's also very flexible if you would ever like to extend the phase space. Like maybe it would be interesting to see if one could predict the number of parked bikes given a bank holiday or given weekend, and all these aspects could be added to the random forest relatively easily. And that's now the outcome. So I show the measured data. Well, that's been data that hasn't been seen by the model before. And I show that data here, and then the densely covered phase space prediction of the machine learning model here. And you can see that the color trends, they correspond quite well to each other. Like you can, for instance, see smaller numbers or larger parked numbers in the regime of small temperature. And also from a quantitative perspective, the prediction is quite decent, as the square root of the mean squared error corresponds to roughly 1/10 of the average value of the parked bikes, which again in this context is quite a decent prediction performance given how naive the approach was in general. Okay, I did a bit more on machine learning, but I'm not showing that here. I calculated the Markov steady state for the same data essentially, and if you're interested in that, well, feel free to check out this link here. Okay, last but not least, I would of course like to come to the summary for Anna, me, and maybe other students. So first of all, what I did was to scrape Nextbike data in Marburg in order to find which stations to potentially avoid when you're in desperate need for a Nextbike. And for that, I calculated the probabilities of empty stations and found that the larger the station, the less likely it is to run out of bikes. So the general recommendation from my side would be try to find large stations if you're in desperate need for a Nextbike. And feel free to go back to the interactive map to see the locations of these stations, which is quite interesting in itself, I would say. And then I turned towards the perspective of a city and investigated a bit the usage patterns of Nextbikes, and therefore representative, most likely also cycling in Marburg, where I calculated the day-hour usage. So when is the system quite busy in general, the most popular routes, which might be of use for city planning, and also social, economical, and ecological benefits of the whole system. Last but not least, I showed that more precise predictions are possible when maybe a statistical statement is not enough and you would like to do per case predictions. Last but not least, I was fortunate enough to work with Asta Marburg, in particular Lukas and David. Thank you very much for your trust in that project, where we try to optimize the placement of the bikes in the future. The take-home messages are now, first of all, bikes are amazing, and not only are they amazing for you and the environment, but also for your wallet. So you save essentially money on gas. And also, I would like to highlight that those data-driven optimizations of public transport have the potential to increase the quality of life of many of us at a moderate cost. So again, I would like to come back to a case where maybe a city would like to improve bike infrastructure but doesn't have enough money to do it in one go. So then it might be interesting to first find in a data-driven way which combinations of now in Nextbike terms maybe stations or in general streets are popular, and then these might be worth being fixed first with a limited budget. Okay, if you're interested in more, I was very fortunate to be able to speak at the last RC3 already about data in Marburg, but last year I spoke about parking in Marburg. And if you like to, well, read the blog articles corresponding to that, or just see the official CCC video, just follow these links shown here. Thank you very much for your attention. If you have anything to get in contact with me, well, reach out to my email address, maybe some ideas on how to improve a talk or what else to evaluate. And then all the supplementary materials that I mentioned and what I've shown here can be found again on this link here. In particular, thank you very much to all the people who reached out to me based on my last year's talk. I haven't come about to respond properly, but I'm 100% certain that I will do so. Thank you very much for your attention and have a good year.
All right, welcome back. It's time for the Q&A now. You probably know the drill, but I'll repeat it anyway. If you're on Twitter or on Mastodon or on the Fediverse in general, the hashtag is RC3CWTV to ask any questions. And if you're in the Hackint IRC, the channel name is the same, except there's a dash in between the RC3 and the CWTV. And we apparently already have some questions, so I'll just get started now. First question, is the Nextbike API free to use? Does Nextbike even know that you did the scraping?
Yes, so as far as I know, the Nextbike API has been reverse engineered from the iOS app, and there's a GitHub repo by U-Bahn Verleih, and he documents lots of APIs of public transport companies like Nextbike or some companies that also produce the scooters. And since it's the official iOS API, it's more or less public, so to say. It's free and it's pretty much quota unlimited because normally all the iPhones access it. But again, I can only recommend the U-Bahn Verleih repository on that, on GitHub.
And you don't need any credentials to access it?
No.
Okay,
and
cool.
Actually you can, as far as I checked, you can pretty much access the whole world. So you can access stations in Poland, in, well, all of Germany. No.
That's cool. It's probably accidental, but it's quite cool anyway.
Yeah.
Okay, what software did you use for the machine learning stuff?
The machine learning stuff has been done with Python and then specifically with sklearn,
Yes.
which is a quite popular machine learning framework for Python. Yeah.
The working horse of the machine learning community,
Yes.
I would say.
Exactly, yeah.
Do you know if Nextbike adds or removes bikes from the stations, or do they relocate the bikes? Or do they do that, or does it just happen as an emergent behavior?
I would say that, so I had the chance to speak with a person of Nextbike while I was working for the Marburg Asta, and he said that first of all it's not very technical yet, well, not very digitalized yet, and they essentially drive around. So I'm pretty sure that they certainly collect bikes that need maintenance, but then logically probably also relocate them where necessary. No.
All right. Okay, someone wants to know if the scripts that you use will be public. I assume the main part with the API is already answered if you gave the GitHub repo, but are you planning to open source anything else?
Potentially. So I have no plans on doing so just because it's additional work, to be honest. I can just do the same, offer the same thing as last year. Just write me an email, and if there's enough people who are interested, I probably strip down my internal repository. But since in the internal repository there are a few private nodes, that one is not published for sure. No.
All right. Anything else? Dear listeners, you have maybe 30 seconds to comply. So there's one question about the time period of data that you have, but I think you answered it in the talk, right?
Yes, it's more or less whole 2020 and half to 2/3 of 2021. that I collected.
Okay, so you probably mostly have like pandemic situations.
Yes,
which is probably
exclusively, pretty much. Yeah.
I wonder if that's more or less usage than usual. I mean, it's less people having to go places, but more people wanting to not use public transport.
Yes. So based on my data, I can see that it's the number of parked bikes, and therefore the usage is going down. So the number of parked bikes is going up. Therefore, the usage is going down, and that was also confirmed internally by some Nextbike people. Yeah. One more thing. So regarding the people who are interested in the code, regardless of if I am going to publish it or not, if you have questions, just drop me an email. I mean, writing the scraper in particular, it's absolutely trivial. And if it's not trivial for you, then the code wouldn't be of value to you anyway.
All right. How does your data interpret broken/unavailable bikes at a station? I mean, can you see that? Or do you take it into account?
Yes, so I don't see it directly. I mean, I have a list of all the bikes. And if I would a little bit deeper, I could probably, compile a list where I see where a particular bike is standing at the moment. And if that bike would be, for instance, absent for a longer time, I could conclude that it's maybe broken, maintained or something like that. But there's no direct data on that. No.
All right. Do you think that Nextbike moving the bikes has somehow biased your data? Like if they relocate them?
That's a good question. I have absolutely no idea. So I mean, what I did calculate was that so I defined a term a term of activity. I defined it as the number of bikes coming in divided by the number of bikes going out plus the number of bikes going in. So it's, so to say, the activity. And when that number, it's obviously between 0 and 1. And if it's far from 0.5, that would mean that the station runs empty, essentially, or overfills at some point. And there are a few stations where it's a bit above 0.5. But of course, that's only the data that I used has only the moved bikes incorporated already. So it's not really something that could be used for really trying to find that. No.
Is this kind of data also available for bike sharing services that don't have docking? If they even exist still in Germany, I kind of lost track. I think maybe they all went bankrupt. But
docking, what do we mean by docking?
By they don't have fixed stations, but they're free floating.
Mm-hmm. So I mean, all that I did was to look at the stations, but actually there are a few freestanding ones also in Marburg, and these people are typically penalized by money, so they have to pay a fee. I didn't analyze it at all. Would be interesting for sure. And as far as I know, there are cities where it's completely where there are no stations for Nextbike, where people can drop it off wherever they like. Don't quote me on that. It's just something that I heard. Most likely in the large cities, so maybe in Berlin could be.
Yeah, I think here there's like some locations where you have to drop the bikes, but I'm not sure if that's Nextbike. I can never remember which ones I actually end up using. All right, everybody. Now is your last chance to ask more questions. I feel like a teleshopping, like the RC3 teleshopping, which I highly recommend if you haven't checked it out. It's probably the peak experience at the Remote Congress is the teleshopping channel. And you should all have a look and maybe buy some extremely useful items that they sell. Okay, so the chat confirms that Nextbike does have cities without stations.
Yeah, very good, yeah. Yeah, and I mean, I can only, if you're remotely interested in all these public transport data studies, definitely check out the U-Bahn-Verleih GitHub repository. There's a large number of systems documented there.
Okay, and that's just U-Bahn-Verleih, just as you would write it.
Yes, let me look it up very quickly. U-Bahn. So the person is from Ulm, and he also contributed to the CCC infrastructure. His name is Konstantin, and yes, it's U-Bahn Verleih. And I think
Okay.
it's like, I think the repo name is Wobike, as far as I know, but.
All right, good, thank you. All right, I think we've managed to exhaust the internet. So people, where can they find you if they have any further questions? Are you going to be wandering the world, or what it's called, you know, the...
Oh, that's a good idea. I haven't planned, but I can. So I have no idea how it works, but I'm sure I can figure it out. So, I mean, in general, drop me an email, and you can find my email on lelep, LELLEP.xyz. It's my website. Other than that, I could be online in the 2D world adventure now, if that's of value to anybody.
People can maybe hunt you down if they really need you.
Definitely, yeah.
Okay, wonderful. Well, thank you for your talk and for answering the questions. And thanks everyone for tuning in. Have a good remainder of Congress. I think you should be able to, at some point, rate talks in the Fahrplan, if that feature still exists. So if you want to see more of this kind of stuff, maybe leave some feedback. Bye-bye.
Bye.